Hello and welcome to our lesson on the structure of the atom. So let's move into the build part of our lesson where you are learning new information. You need to know the definition of the word atom. What is an atom? An atom is the smallest particle of a chemical element that can exist. The way I tend to think of it is a bit like a building. If you break down a building to its smallest parts, you get down to a brick. You might split that brick in half, but you've only got half a brick. The brick is the smallest part of a house. In a similar way, an atom is the smallest part of any chemical element or any chemical substance that makes up the rest of the world. Now, the word atom comes from the Greek meaning indivisible, meaning it cannot be divided. And the reason we think, or the reason we call it this, and the reason we thought it was the smallest particle was because this name was given to it way back in 460 BC. So that's 460 years before the birth of Christ. So you're talking 2,500 years ago, where we didn't have microscopes and we didn't have labs and we didn't have a lot of understanding about chemistry or about the world around us. And Democritus here, picture Democritus, thought an atom was the smallest thing you could have. And that's where it gets its name from, atom. So when you think of a periodic table, we've talked about this in year 8, you talk about elements, chemical elements. I've highlighted oxygen there for you, but an atom of oxygen or an element of oxygen, sorry, could be made of one atom of oxygen, it could be made of 2 atoms of oxygen, it could be made of thousands of atoms of oxygen, but it's still the same element. Okay, so an atom, the smallest particle of a chemical element that can exist. Make sure you've got that written down. So how big is an atom? Well, that's like asking how big is an elephant. Which elephants are you talking about? Well, atoms are all different and each element has a different size atom. Hydrogen here you can see is very small. Oxygen is a bit bigger. Carbon is a bit bigger still. Some of the other elements at the end of the periodic table like uranium and plutonium, well, they're much bigger still. For an atom, the average size of an atom is 1 × 10 to the -10 meters. That's 1 nanometer. And that's the number you need to know. Write it down. The average size of an atom is 1 × 10 to the -10 meters. They're tiny. So we used to think atoms looked like this, a solid sphere that was not able to be broken down into anything smaller. But we know this is not true anymore. We now believe the atom looks a little bit more like these pictures here. Now, these are not all the same, but they are similar to each other, aren't we? And there are a couple of things that are the same in each picture. First of all, we have a central area, which we call the nucleus, and that nucleus is surrounded by moving electrons. Now, these are all models of the atom, and models are there to help us try to interpret or try to understand things that may be too big in the real world. So you think about the solar system, it's really very difficult to understand how far away the Earth is from the sun, so we use models to try to explain it. In this case, the atom is too small for us to see, so we make models so we can understand the relationship between the nucleus and the electrons. Sometimes we use models to explain things like too fast, like a chemical reaction, or really slow, like a really slow rust chemical reaction. Or something that's really complicated and we want to simplify it to help us understand it. So models are really useful. The big problem with these models is that they do not show us that an atom is 3-dimensional in space. These are just 2-dimensional pictures. In reality, atoms are 3-dimensional. The other thing I want to just pause and take note of, guys, I think it's really important you understand this, is these black lines that you can see in the diagram here, the circles that we've drawn, show the path of the electrons that are moving. They're moving electrons, they're traveling around the nucleus, just like the Earth moves around the sun. They're not real lines in space, though, are they? So the best example I can think of is this diagrams here. You can see here you've got pictures of the planets going around the sun, and you can see those lines again, can't you? Now those lines, if I went up into space, you're not, you know, the lines do not exist in real life. The lines are simply there to help us understand the path that the planets are traveling around the sun. And in the same way, the lines in our diagrams of the atom show the direction, the travel of the electrons around the nucleus. So we know the atom is actually made up of smaller particles, or what we like to call subatomic particles. And you guys need to be able to draw atoms in great detail. So let's have a look. So the first thing I would draw is the nucleus. That's the center of the atom. Now, in some diagrams, this black line is not drawn in. You don't need it, I suppose, but I tend to draw it because it helps to separate the different bits later on. You'll see what I mean in a minute. Inside the nucleus, we have two types of subatomic particles. We have protons, which are coloured in yellow, and we have neutrons, which are coloured in green. I'm going to come back to the detail about these in a few minutes. Now, around the nucleus, we have these lines that we're going to talk about. So you could have one, you could have two. I've only drawn two today. You can have up to 6, 7, but we don't tend to draw that many. I've drawn two today. And remember, they're not real. We draw them to show where the electrons are travelling. But these are called electron energy levels, or they're sometimes called electron shells. Now, on these energy levels, you have the electrons, and you'll notice the electrons there are much, much smaller than the other two particles. Now, remember what I said, this is a model. It doesn't show that it's three-dimensional, and nor does it show that those electrons are actually moving around the nucleus. So the first bit of information you need to know about the subatomic particles is their mass. Now, mass is normally measured in grams or milligrams or micrograms, but these subatomic particles are so small we can't really measure them accurately in that way. So what scientists did is they compared the subatomic particles to each other. So for example, a proton, we say, has a mass of 1. 1 watt isn't relevant. We can't give it a unit. It has a mass of 1. So if we compare it to a neutron, they are the same size. Neutrons also have a mass of 1. They are the same size, so we've given them the same number for the mass. Now, when we compare them to electrons, electrons are much, much smaller. So do they have a mass of a half, a mass of a quarter, a mass of 0.02? No, they're really, really, really small. Compared to a proton and a neutron, an electron has a mass of 0.0005. It's tiny. In fact, when we talk about the mass of atoms, we don't even measure electrons because their mass is so small, it's irrelevant. You need to know those numbers, guys. Write them down. So the second fact you need to know about is the electrical charge of these subatomic particles. Now, it's a weird thing to think about electrical charge, but it's simply how an atom or how a substance or how a particle behaves when you put it in an electromagnetic field. So does it go one way, positive, or does it go the other way, opposite, negative, or does it do nothing, neutral? And that's what those three things mean. If that confuses you, don't worry, just learn the facts. So a proton, I think is the second one, hang on, a neutron has no charge. So if you put it in an electromagnetic field, it would do nothing. It wouldn't be attracted to the positive or to the negative. It has a neutral charge, so 0. And that is why you can see in the N, I've put a little O next to it for 0 charge. Now protons, P for protons, P for positive, they have a positive charge and it's a +1 charge. In comparison, electrons have a negative charge. So we say they have a -1 charge. Sometimes you will see electron written as E for electron, -1 because they're always negative. I sometimes joke that if I was going to be a subatomic particle, I'd definitely be an electron because I'm small and I'm negative. My students tend to agree. So let's look at the transfer element of this lesson. So using your knowledge and applying it. How are you going to use this information? Well, often you're asked to fill in one of these tables where you're given the subatomic particles, the protons and neutrons and electrons, and then you're asked to fill in the mass and the electrical charge. You might think that's nice and easy. However, they like to trip you up by rearranging the subatomic particles and by rearranging the headings. So you'll notice in the first one I've got protons, neutrons, electrons, but in the second one I've got protons, electrons, neutrons. So they've muddled it up so you guys can't just write down the same numbers in the same boxes every time. You've got to be careful. You've got to know your stuff. This table is traditionally done extremely badly. So if you can get this right, you're onto something. Now, how do they extend this knowledge into and make it a little bit harder? Well, sometimes they also ask for a location, and that simply means where would you find that subatomic particle? It's either going to be in the nucleus, so the protons and the neutrons, or it's going to be in the electron shells or the electron energy levels. This is a question that is asked often. Let's look at this question. It says, what is the electrical charge of the nucleus? So you're looking at this diagram, you've seen this diagram before, okay, and you've got an atom, and you can see you've got protons and neutrons in the nucleus, and you've got the electrons in the energy levels. But the question is asking about the nucleus. Now the nucleus, the inside bit, only has protons and neutrons, okay? And the nucleus then always has a positive charge, always, doesn't matter what atom it is. The nucleus, the middle bit, is always positively charged. We've got neutral neutrons, so we can ignore them, and we can add together the number of protons. 1, 2, 3. So this atom has a positive 3 charge in the nucleus. Now watch what happens here. Look at the question again. What is the electrical charge of the atom? One word difference, but they do this to confuse you. Now the atom is the whole thing. It's not just the nucleus, it includes the energy levels as well. So now we have 3 positive protons and we also have 3 negative electrons. So you can see the diagram there. I've got +3, I've got -3. If I add those together, they cancel each other out, don't they? +3 -3, and I end up with 0 charge. And so an atom always has a neutral charge. Golden rule here, guys, we'll come back to this next week. An atom always has the same number of protons and the same number of electrons. So they always cancel each other out, and you end up with an atom of a neutral charge. So that is the end of the lesson for today, guys. I want to leave you with this image. I've been using dual coding with some of my classes for a while now, and it really seems to help. Trying to pick one image which summarises all our learning for today. So here's the image. I've got positive protons and neutral neutrons, the same mass, same size, inside the nucleus, and I have the much smaller negative electron on the energy levels. I've also included that table. It's so vital that you now have that information in your memory. It'll really help with your chemistry and it'll really help with your physics as well. That's the end of the lesson today, guys. Thanks very much for listening.